This morning, I'm going to talk to you about cloud-adjacent databases and how they can facilitate migration to cloud. And maybe some of you will say, what's a cloud-adjacent database? Well, I'll start by explaining what that is. It's probably helpful. So this is kind of the outline agenda. Look at some of the challenges of migrating to the cloud, explain what cloud-adjacent databases are and how they can help in some scenarios. Then I'll give you an introduction to the Oracle times 10 in-memory database because, as you will see, I think that's a good candidate for the role of a cloud-adjacent database. Then I'll cover a couple of example use cases and then wrap up questions. A little bit of terminology first. I'm sure you guys all know these things, but just as I'll be mentioning some of this stuff during the course of the presentation, it's always wise just to make sure everyone's on the same page. So, multi-cloud. That's an environment where your application or system or service is deployed across or uses resources from multiple independent clouds, okay? And we are seeing a bit more of that now. Hybrid environments, these are actually relatively common, particularly when you're in the process of migrating from on-premise to the cloud. That's where you've got some of your stuff in the cloud, some of your stuff still on-premise, and some interaction between them, okay? And then, of course, there's edge computing, which in some ways is almost the opposite of cloud. With cloud, you're kind of centralizing everything into the cloud, even though the cloud is itself a little bit diffuse, perhaps. Edge computing is the opposite. It's where you're decentralizing everything and pushing compute resources closer to where they're needed, okay? And these things all interact and interplay to some degree. So obviously, cloud's a huge thing today, and everyone is trying to figure out, should they go to cloud? How can they go to cloud? What's involved in going to the cloud? And all the difficulties or benefits associated with doing that. Let's be real, there are some challenges in moving to the cloud, okay? It's not just, oh, I'll just put the stuff over there and everything is fine, right? There's a lot more to it than that, You need to think about the architecture. It may well require you to make some architectural changes moving to the cloud, okay? Depending on your application. Certainly, performance is something you will need to think about, okay? Cloud, by definition, is some way away, network-wise, and if getting in and out of that cloud involves network latency that you typically don't have for on-premises applications, okay? And what's the approach? Can I lift and shift everything? Can I do it one app at a time? Do I need to have some sort of hybrid setup as part of my transition? Many different things to think about, okay? The key thing here, and really one of the focus areas for what I'm talking about today, okay, is within a data center, your typical network latency is sub-millisecond, quite often sub-millisecond, okay? From the outside world into and out of a cloud, you're typically looking at tens of milliseconds, okay? So we can actually have, 2 orders of magnitude difference here in network latency, which may well matter, particularly in a hybrid model, okay? So if you've got a latency-sensitive application or a heavily database-dependent application, you've got to think very carefully about where do I put things and what could be the impact of the network latency on that, particularly if you're going through a transition architecture for months or years as part of your migration where you're separating the app and the database, for example, okay? So let's try to illustrate that with a picture, okay? So that's a fairly typical kind of on-premises environment at a high level. Got some databases, app servers, applications, users. Obviously, the users may be outside the data center, but the bulk of the compute and data storage and everything else is in your data center, traditional on-premise. Yeah. The nirvana that, in theory, everyone is trying to get to, maybe, is we would simply move all that and put it in the cloud. That's the simplistic picture, okay? But of course, to get from there to there, for some period of time, you'll probably have some kind of setup like this, right? You'll have some stuff still on-premise, some stuff in the cloud. And that doesn't look too bad, but in reality, of course, you'll probably have all that kind of stuff too, right? Depending on your applications and how interdependent they are and everything else, right? It can be quite challenging. And, you might think, well, that won't persist very long, but you might find that this middle setup actually hangs around for months or even years or even longer. Okay? So there's some challenges, right? So we have this notion of a cloud-adjacent database, and this is a fairly new term, and I think actually Oracle made this term up, actually. I'm looking around, I haven't found anyone else really using this. But it's a very simple notion, actually, okay? If you put a lightweight database close to the application, by close here we're talking about in terms of network latency, okay? And that database can contain the majority of the data that the application needs, certainly all the high interactive data that the application is constantly accessing. And then you can somehow synchronize that data with the main database out in the cloud or whatever. In the background, you essentially hide the cloud access latency from the application to a large degree. And you actually offload some work from the main database as well as a second bonus, okay? So the idea here is that this will lead to faster and more predictable application responsiveness and potentially improved reliability as well, because you're less dependent on the wide area network across the internet into the cloud, okay? And you might say, well, isn't this really just an edge computing, edge database case? Yeah, you could think of it like that, okay? Pictures are always nice. So here's kind of that hybrid architecture, very simplified, of course, without any cloud-adjacent databases. And you can see that from the user's perspective, when he's interacting here, the minimum latency for any request that he makes is going to be 2A plus 2B, in and out, okay? And B here is, tens of milliseconds, whereas A is very small, okay? So you can imagine, that isn't particularly great for performance, okay, and response time. So how about if we did this? We deploy some cloud-adjacent databases, whatever they may be, on-premise, near to those applications. And those databases contain a large working subset of the data needed by the applications, maybe all the data, maybe not all of it, but a large subset. And they synchronize bidirectionally that data with the cloud-hosted database over there, the cloud database service, whatever it might be. Now, the latency that the user sees is 2A plus 2C, and C is much, much less than B. It's a very simple premise, yeah? There's no magic here at all, okay? Similar idea with multi-cloud, okay? Here the application is in the cloud, but it's accessing databases that are in a different cloud. Same problem, which you could potentially solve by doing that. Exactly the same premise, okay? So this is kind of the notion here. So if we want to do this, what are the sort of characteristics we want for those cloud-adjacent databases, okay? They really need to be lightweight, easy to deploy and easy to manage. The whole point about moving your database and everything else into the cloud is to simplify things, reduce complexity, reduce management overhead, all that stuff. If you start deploying complex databases on-premise, you're not really solving that problem at all, right? You're just making it more complex, in fact. So they do need to be lightweight, simple, easy to manage. Clearly, you're putting them in between the application and the real database, so they need, from an application perspective, to look, feel, and behave just like the real database, okay? So they need the same APIs, the same SQL, largely the same functionality. Okay? Ideally, they'll also have good performance, okay? It's great that we're hiding the network latency, but, a lot of application activity is going to run against that local database. It needs to be able to perform well. And because the application is relying on it, and the data in it is almost certainly important data, it needs to be persistent, recoverable, possibly even highly available. So, having set the scene, let me introduce you in a few slides to one member of the Oracle in-memory database technology family. So Oracle has a bunch of in-memory technologies, all the way from Exadata storage through Oracle database in memory. But the one today, of course, that we're talking about here is my product, the x10 in-memory database. Okay, and I'm going to just take a few slides to introduce you to this, because I suspect if I ask you the question, who here has heard of or used x10, will anyone actually be able to put their hand up? Way! That's unusual. Somebody's actually heard of it. That's cool. So x10 is actually a very mature product. It's actually been around about 20 years. And it was actually the world's first commercial relational in-memory database, believe it or not. Okay? Obviously, it's evolved a lot in those 20 years. We were actually acquired by Oracle in 2005. Before that, we were an independent company. So the product as it stands today, you can deploy it in 3 different ways. It's one product, it's one installable thing, but you can choose when you configure it 3 different modes of operation. You can use it as the database of record, and if you do that, you will typically also use the built-in high availability via replication, because if it's the database of record, you generally want to be really sure that data is well protected. And a lot of our customers do that. If you have an existing Oracle database, but you want to improve the performance of certain aspects of that, you can deploy x10 as a cache for that Oracle database, where you will cache some subset of the data, and I'll talk a little bit more about that later. Okay? That cache can also be highly available using the built-in replication. And in these configurations, you will typically be able to see microsecond level response time for SQL operations, both read and write. And depending on your hardware, we can typically scale up on a single system to in the region of millions of transactions per second. Typical in-memory database levels of performance. Okay? Slightly newer feature that we released, generally available last year, you can now also deploy x10, typically as a database of record in this case, as a fully distributed, elastically scalable in-memory database. Okay? That's obviously focused rather more on huge storage capacity, because you're able to utilize the memory of many machines instead of just one, and throughput. So you still get millisecond response times, but that's millisecond, not microsecond, as our friend earlier today said. Don't get confused between milliseconds and microseconds. But you can get up to sort of millions of TPS if you have enough hardware to throw at it. Okay? And as we'll see in a couple of slides' time, it's elastically scalable, fault tolerant, and all those other things. So looking at x10 Classic, so that's the singleton or the replicated version. It's a pure in-memory database with standard SQL, PL SQL APIs, okay? So it looks and feels very much like an Oracle database, except it's not the big Oracle database. It's ASIC compliant, it has transactions, isolation, persistence, all that stuff, okay? It is persistent and recoverable. So although it's in memory, it does usual sort of checkpointing, transaction logging to local storage. So if the power fails or something else, you can restart everything, it all comes back, loads up into memory, and everything's back as it should be, okay? It's very fast because it's in memory and it's been built from the ground up for speed, and particularly good for latency, very low latency. And it has HA through replication, either for local HA or disaster recovery or both. And that's again designed for very high performance, so it's highly parallelized and everything else. So that's x10 Classic. And that's the sort of performance you typically get. So this is key-based lookup or key-based update. Those are microseconds. Okay, less than 2 microseconds for a key-based select, and about 5 microseconds for a key-based update. That's fast. That same thing, x10 Classic, as I said, it can be deployed as a cache for the Oracle database. Okay, and this is a very powerful capability. It has a lot of built-in functionality specifically for this use case. Okay, it allows you to cache a subset of the Oracle database. You can cache the whole Oracle database, but typically that's not very practical because that may be many terabytes of data. So you can choose particular tables and even subsets of tables that you want to cache into the times 10 database, and then times 10 will maintain the synchronization. And those cache copies can either be read-write, so you can actually transact against them, or for some use cases, you might want to make them query-only, okay? And you can choose this on a table-by-table basis. Okay? So there's an example of how you define a cache group within times 10. So a cache group is a SQL object you create with a SQL statement, and that defines either a single table or a group of related tables that you want to cache from Oracle to times 10. You just execute a SQL statement like this, and then you will see that inside times 10, you will have a table called OE customer with these columns, and the data in that table now reflects the corresponding data in the Oracle database. If data changes in Oracle, it's reflected automatically in times 10. If it's a read-write cache, if you modify the data in times 10, it gets reflected back to Oracle. Okay? So it's very easy indeed, right? It's just declarative. You just create those objects.
So is it read-write through or write in a bind?
You have a choice, actually. You can configure either, okay? So we have synchronous propagation or we have asynchronous. People usually use asynchronous because it's much faster, okay? But we actually support both, in fact. So. And then just a little bit about scale out. So this is, as I say, a relatively new feature, came in last year, but we're seeing a lot of interest in this now from customers. We've already got a few production deployments and a whole bunch of POCs going on. So basically, we took the concept of times 10 Classic, obviously made a lot of enhancements to that to allow us to basically turn that into an elastically scalable system. It's a fully distributed, shared nothing in-memory database with transparent data distribution. So the application just sees one big database. It doesn't know that it's all distributed and split up and the data spread around under the covers. It sees a database, it sends SQL in, we process it and give the answer back, okay? It's got a single point for management and administration. It can support parallel SQL. It's really quite sophisticated, and we're adding a lot of new functionality to this now in an upcoming release, and this will probably be our focus area for the next few years, is the scale-out product in terms of adding new functionality. And clearly, you can achieve very high levels of throughput with this. Okay, so this is a very familiar YCSB, Yahoo Cloud Serving benchmark. Okay, it's a sort of a key value benchmark, but it's a nice way of demonstrating scalability of cluster databases. And you can see as we increase the number of nodes in the cluster, we get up to about with 16 by 2. So the 2 means we have 2 copies for high availability. Okay, so that's a 32 node cluster. And we get up to 38 million operations per second. That's per second, per minute or per hour per second. Okay? Other benchmarks, we can actually show even higher numbers than that. So I just want to give you a flavor of the times 10 family, because clearly not many people know much about it. Why have I bothered to tell you this? Well, I think, if you're thinking about this cloud adjacent kind of architecture to improve your performance, and particularly if your backend database is an Oracle database, then times 10 Classic in its cache configuration is really a very good fit for this, okay? Because it is lightweight, it's really easy to install, very easy to deploy and manage, doesn't need a DBA, but it looks and feels like an Oracle database, which is great. It's certainly high performance, there's no question about that. And if your backend database is Oracle, we have that caching mechanism which can do the synchronization out of the box. You don't have to build anything. Yeah, you simply choose what you're going to cache, how you want to cache it, execute a few SQL statements, and off you go.
How do you deal? Do you have a joining between your cache and non-cache tables?
So there are some limitations around that. Okay, you can't do joins, so you need to choose carefully what you cache, right? You need to make sure that we have a mechanism that if you try and do that, a join between a cache table and a non-cache table, we will transparently pass that through to the back end and execute it there, but that'll then be slow, right? Maybe it doesn't matter for the occasional operation, right? Yeah, but as with all these things, you do need to think a little bit about what am I going to cache and what makes sense and what doesn't, okay? Even if you're not using Oracle as a back-end database, times 10 actually has some other functionality that can enable you to fairly easily build your own synchronization. So we have a very high performance log mining and event notification API called XLA, for example. And we have customers who've actually used this to use times 10 as a cache for a non-Oracle database. Obviously, we don't necessarily shout very much about that, but Sybase, DB2, whatever in the back end there as well. So that is possible as well, but it's not out of the box. You have to do a little bit of coding to get that up and running. So it's kind of got the right characteristics. So let's look at a couple of actual example use cases, okay? So this one is, we're just starting sort of quite a large POC for this one, so it's not in production yet, we're just in the early stages. It's with a large Japanese automotive manufacturer. I'm not allowed to say who they are, but it's one of the big names. And basically, they have a need, they want to capture data from all the sensors in the car. Modern cars have a lot of sensors, GPS, various other, is it raining? The windscreen wiper's going. What are you listening to on the radio? All these kinds of things. Okay, so they want to capture that data, do a bunch of processing on it, push some information back to the car to support things like navigation, traffic alerts, where's the nearest parking space, all those kind of great things. So this is the sort of thinking that they have, right, around the services they want to provide. And obviously this thing needs to be reasonably fast, okay, particularly for navigation. It's no good telling you that you're now in a traffic jam. You kind of want to say, I need to reroute before I get to the traffic jam. And it needs to be fairly resilient as well, obviously. So their initial idea, and we were talking about them with this, was, put stuff in the cloud. The cloud is great, right? You have a database there, you can have the various applications that do all the processing, and we have the internet, and over the mobile network, the car systems can communicate, and that'll be great, right? Well, okay. You can see the problem here, right? There's the internet, there's a lot of latency here, right? It's not always super reliable. So we kind of ran some numbers and did some things and thought, yeah, that's maybe not the best solution. What options do we have? So we suggested, well, something we could try. We could deploy a lot of edge systems, if you like, okay? Small units containing a times 10 in-memory database, some local application logic, okay? We could deploy them close to network access points, okay? You could synchronize times 10 with the back-end database using the cache feature. And then the cars can interact with their much closer, in terms of network latency, roadside interaction system, okay? So the idea here, right, is that the vehicle will interact with the nearby RAS. It'll send in its data. That data will be locally processed to some degree. Some of it will be synced back to the central database. It may get heavier crunching. Obviously, the central database has the big picture of everything, and it'll then put some data in its database which gets synced back to those local systems, which can then be pushed back as required to the car. So that's kind of the high-level idea behind this, and I say we're just starting to build this out now and do some trials and things. It's very early days. But, and the second one, which is more of an internal thing to a certain degree. So you may have heard, there's been a lot of shouting about it in the press, it's Larry's new toy, the Autonomous Transaction Processing Cloud Service, the Oracle Autonomous Database and all that great stuff. That's a cloud service. Okay? It does offer really good performance, but it's a cloud service. If you want to access that from something that isn't in the same cloud as that, you have the usual latency issues. So we can solve that in two ways. If you have on-premise applications that want to talk to the Oracle ATP Cloud Service, then we can do what we did earlier with times 10 as a cache locally. If you have stuff running in one cloud data center, maybe hopefully this is the Oracle Cloud, and you're accessing the ATP Cloud Service in a different data center, we can actually provide this as a service, a cloud service for you. Okay? It doesn't exist yet, but it's something we're actively looking to work on and productize maybe next year. So just to kind of summarize, well, that didn't take as long as I thought it would. There are a bunch of risks with migration to the cloud, or potential risks, and performance reliability can often be one of them, okay, particularly if you have that kind of hybrid model. Our suggestion is that cloud-adjacent databases, as we are calling them, can help for certain types of application where they're suitable. They'll certainly improve your performance and reliability, but they certainly do make the architecture a little bit more complex. So there's certainly a trade-off there. Okay. If you're going to go down that route, probably you should certainly think about an in-memory database as the cloud-adjacent database. They're usually a good fit. I mean, typically you're not caching the entire back-end database. You're caching the data for a specific application or subset of an application. So the data volumes are typically pretty manageable, maybe hundreds of gigabytes perhaps, rather than tens of terabytes, but it does depend on the application. Most in-memory databases tend to have lightweight footprints, apart from the memory requirement, and a low oversight, and they give good performance. Okay? The key thing you do need is some method of data sync. Okay? So you need to choose a product that provides that in an easy-to-use fashion. So out of the box, if your backend is Oracle, times 10 is a great choice because it does that. If you have some other kind of backend database, then you need to think about how you want to do that. You may need to build it yourself, or maybe you can get a product that actually supports that backend database as a target. So that was really my talk. Any questions? Anyone about anything? Yes?
Could you explain about the cache, the way this works as a front-end cache? Does that mean you're doing local commits against the front-end cache database and then another transaction to commit things to the database?
Yes, so if you do, that applies if you're doing read-write caching, yes? Okay, obviously it doesn't apply for read-only caching. For read-write caching, there are two choices, as the gentleman here asked, okay? You can configure us for what we call synchronous write-through. So you do some transaction work against times 10, and then at some point you commit, okay? With synchronous write-through, we first push the changes to Oracle, commit on Oracle. If that succeeds, we commit locally. So that guarantees things stay in sync. If the commit on Oracle fails, return error, you roll back, right? So either it happens or it doesn't, okay? But that's relatively slow, of course, right? Because you're still having to go to the backend database. So the more common scenario is what we call asynchronous write-through, which, as the name suggests, is kind of how you described it. You transact in times 10, you commit, it's committed in times 10, it's now protected by the times 10 persistence recovery mechanism, by the times 10 HA if you've configured that. And then asynchronously in the background, we capture those changes out of the times 10 log stream, usually the in-memory part of that, so it doesn't have to go to disk. And then we propagate those changes to Oracle and apply it there. So that means that Oracle is always a little bit behind the cache. That usually doesn't matter unless you've got things also looking at the Oracle data and they need some sort of consistent view. The big benefit there is it's much faster, of course. And it does isolate you again from a dependency on the network connection between the cache and Oracle, okay? If that connection goes down, you can actually continue to transact in the cache. The stuff is there in the logs. When the network connection comes up, we'll start grabbing it from the logs and pushing it down to Oracle. So,
what do you get to do about conflicts in that case?
So as soon as you add conflict resolution in, that slows everything down, right? So we don't do conflict resolution. We say, if you're going to do that, you need to route the writes for that table, or at least the subset of data. All the writes need to go through times 10, okay? Now, there are ways around that, okay? You can have that push-through, depending on the application. You can have that push-through table push into a separate table in Oracle with a trigger. That trigger can then apply to the main table, and you can put your conflict resolution there, okay? But that's something that you have to think, what sort of conflict resolution makes sense for my application, right? And then you put it in there. So there's different ways of architecting this stuff, yeah. Yes?
A few questions. So when you have the times 10 database local in the cloud connector, can you have foreign key constraints to the tables on the main database?
No, times 10 is just the database there, so everything happens in times 10, right? You can't have a foreign key. If you think about it, that would kind of defeat the whole purpose, because every time you had to check the foreign key, you'd have to do a network hop to the back-end database. You're really not going to...
And then you get the data in there, if you had a table on your main database and, to load all that data in there, you need to do that initially?
Yes, well, actually, so there's two choices there as well, okay? You can either do what we call static caching, which means that after you've defined the cache, you preload the data set from Oracle to establish the cache, and from that point on, the synchronization mechanism takes care of it, okay? That means you guarantee that any data the application is going to touch in the cache tables is definitely in the cache, okay? Sometimes maybe the back-end data set is too large, okay? So we also have this thing called dynamic caching, where for certain types of operation, basically key-based operations, if there's a cache miss, tries to do something it's not in the cache, times 10 will transparently go to the back-end database, grab that data, pull it up into the cache, put it there, complete the operation, return the answer, but now that data is in the cache. So the first touch to that data, if it's not there already, is quite expensive, because you have to go to the back-end database. But subsequent touches to that data are normal in-memory speed, okay? And to support that kind of usage, clearly if you keep pulling data, eventually it's going to fill, right? So we also have a couple of forms of aging, either LRU or time-based aging you can use in that scenario to kind of discard old data out of the cache when it's no longer required. Any other questions?
How times 10 is different than coherence?
Well, it's totally different to coherence, because coherence is an in-memory data grid, yeah? It's about storing objects, primarily Java objects, so it does have bindings for other languages, okay? So the coherence view of the world is I've got a distributed set of memory which stores Java objects. You can store the objects, you can get the objects back. You can actually push some processing into coherence as well if you want to and do some stuff in there. It doesn't have built-in persistence. If you want to persist that stuff to disk, you have to plug in some sort of persistence provider. But the fundamental thing is it deals with objects, right? It doesn't really have a query language. It's not relational. So if your view of the world and your application's view of the world is just a bunch of objects, then coherence is potentially a good fit for you, okay? Times 10 is a relational database with tables, indexes, and SQL, PL SQL, relational stuff. Database APIs like JDBC, ODBC, that's the fundamental difference, right? So our whole view of the world is relational database centric, okay? And if you have a relational database application, it's usually easier to use times 10 than coherence. Yes, if the application does its own JDBC calls and executes SQL, you can't easily use coherence with that, right? So it's quite a clear distinction, really.
Can you use it as a kind of transparent proxy also? So let's say I have caches for certain tables and not for other tables. Can I still query on
Yes.
data?
Yes, you can. As I said, there is this thing we call pass-through, which is another feature of the caching mechanism in times 10. And there are different options for this pass-through, but essentially, imagine a scenario where your back-end Oracle database has 150 tables, 200 tables, whatever, but you've only cached 20 of them in times 10, because they're the performance-critical ones that the application mostly uses, right? But sometimes it needs to access those other tables, right? Obviously, the application could have a separate connection to Oracle, and it could say, oh, actually, I need to use that for this, and that's fine, but it's kind of inconvenient, and you have to change the application. It's got to be aware of where stuff lives, right? So with the pass-through feature, the way it works at a high level is, everything goes into times 10. If times 10 can satisfy that request, because it has the tables and everything, then it does so. And if it doesn't, it simply redirects the operation to Oracle as is. Oracle processes it, something comes back, and we hand it back to the application, basically.
And the payload will be that is coming from...
It'll be whatever comes back from Oracle, yeah.
It doesn't do anything as well, I just...
No, so we don't do anything with it. We simply give it back to the application, right? It might be as simple as success, if it was just like a commit or an insert, or it may be a result set or whatever, right? And the application will process it, you know, in exactly the same way as if times 10 wasn't even there, right? So.
If another application updates the main database and happens to update a row that's also in the times 10 database, does that get pushed to the times 10 database?
So for the read-only caching, yes, it does. That's what we call auto-refresh. So we track those changes inside the Oracle database, and they get refreshed to the cache. Doesn't happen for read-write caching. For read-write caching, you mustn't let something update a row in Oracle that's cached in times 10. So the typically easiest solution for that is to funnel all the writes through times 10. Easy to say, not always as easy to do in reality. I said there is another way around that, is that you can push the writes from times 10 into a shadow table in Oracle, and then you can have a trigger and your own PL/SQL-based conflict detection to merge those changes into the base table if you need to have sort of updates going on there as well.
So from data source perspective, my application needs to know about both the data sources, right? The times 10 as well as the main application.
Well, generally speaking, in most cases, it only needs to know about times 10. If you leverage things like pass-through and everything else, it will typically just connect to times 10, and we will handle everything else. That's the simplest configuration, right? If you want the application also to be able to go directly to Oracle, then clearly it needs to know about both, right? Okay, there's no more. I think we're done. Thank you very much. Ahead of time. Look at that.